Hi, everyone. Welcome to the second half of lecture 1, which is just going to be a review of the math background that will be useful for understanding the theoretical part of this course. So in terms of prerequisites and background that you should be aware of, I have categorized the background into three areas of math. So in particular, you're going to need to know some facts from linear algebra, some material from analysis, namely real analysis, but functional analysis will be a bit useful. And then lastly, you'll need to know some basic probability. And so in this second half of the lecture, we're just going to do a quick review of some useful results from each of these that we're going to be using for the rest of the course. And so I might go a little bit fast because I think some of these things you should have seen in some introductory math courses. But let's begin with some linear algebra. So what would I expect you to know from linear algebra, apart from what is a matrix and what is a vector? The things that I would need you to know are some useful decompositions. So here I'll title this matrix decompositions. And these decompositions are primarily going to be used in the second lecture, and they'll be useful for understanding convergence of gradient descent for linear regression. So how do we solve linear regression? The math that we cover here will be useful for that aspect. So in particular, in terms of matrix decompositions that I would expect you to know, there's sort of two primary decompositions. The first one is going to be this eigen decomposition. And this is, if you're given a matrix A, it's a square matrix, so an n by n matrix, and we say that A is diagonalizable, then we're going to be able to write, then we can write A as the product of technically three matrices. We're going to have Q, lambda, Q inverse. And now this Q is just going to be a big matrix of n vectors, which I'm going to call V1 to Vn. And my lambda is going to be a diagonal matrix, lambda 1 to lambda n. So it has zeros on the off diagonal entries. And the key property of this matrix is that the lambdas from I equals 1 to n are eigenvalues with corresponding eigenvector Vi. And what does this mean? This means that A Vi is just lambda I Vi. So this here is my eigenvalue equation. So why is this useful? Well, first of all, it tells us that there's these vectors that when I multiply by A is just somehow rescaling the coordinates of this vector. So this tells us something about the structure of A. The next thing is that when you have A written as a decomposition like this, there's a lot of nice reductions you can do in terms of products of A or sums of A with the identity. Okay, and so maybe before I get into that, one thing to note is that not every real valued matrix has an eigen decomposition. But in this course, we are going to be working with ones that do, and in particular, if you have a real symmetric matrix, so if you have A equals A transpose, then this matrix is always going to have an eigen decomposition. So in fact, in the symmetric case, we actually have a little bit more. So if A, it's right here, if A is symmetric, So A equals A transpose. Then we can write A as Q lambda Q transpose, where again, Q is this matrix of eigenvectors, and lambda is a diagonal matrix of eigenvalues. Okay, and this will come in handy later when we talk about the singular value decomposition. But let's just give a quick example now of how the eigendecomposition is useful. So let's say we actually consider the case where we're considering matrix powers of A. So I'm just going to multiply, let's say, A with itself twice. So usually this will be a bit of a difficult computation to do if I'm just expanding out and computing all the products of entries of A. But with the eigendecomposition, this is quite easy. If I know that A is diagonalizable, I can just take its eigendecomposition. And I just get that the eigendecomposition of A squared, I just power the eigenvalues. And in fact, in the homework, this is a simple question. If you just take A power K, you're just going to be taking the kth power of the eigenvalues. So this is one nice reduction. Another nice reduction that we'll use later on, and I'll call this example 2 here, and it's small enough, I think, to fit in this corner. So if I just consider, if I know that A is diagonalizable, and I want to understand what does A plus I look like, where I is the identity matrix, well, the best part is that Q times Q inverse is just the identity. So I can write this as Q lambda Q inverse plus Q Q inverse. And this is just Q lambda plus I, Q inverse. So somehow adding the identity matrix really is just adding ones to the eigenvalues here of the resulting sum. So this is great. These are 2 examples of reductions that we can do just with the eigendecomposition. The unfortunate news is that not every real matrix, if we're working over the field of real values, has an eigendecomposition. There's this annoying condition of diagonalizability. This is not true in the complex field. Of course, you can always do this decomposition. But the nice thing is that there's another decomposition called the singular value decomposition, and this is always possible for every real matrix, and the matrix does not have to be square anymore. So this is the singular value decomposition. Okay. So what is this? This is, if I'm given a matrix A, let's say now the matrix is M by N. So here M and N are not necessarily equal. I can always write A as the product of 3 matrices now, U, sigma, and V transpose. And what are the dimensions of these things? So U is an M by M matrix, sigma is an M by N matrix, and V transpose, or V, it's the same dimensions, it's an N by N matrix. And here I can get rid of the transpose. Okay. So what's special about the 3 matrices U, sigma, and V? So U and V are orthonormal matrices. Orthonormal matrices, and then sigma is diagonal. And what do I mean by diagonal? It's a rectangular matrix. Well, let me just go over this. It means that, let's say M is less than N. So I'll have non-zero singular values here, or possibly 0 in some cases. And then I'll have a large segment of N minus M by N minus M. And N minus M by M subblock, that's just all zeros. So it's diagonal in this form. Okay, so before I said U and V are orthonormal matrices, what does this mean exactly? This just means that UU transpose equals V equals the identity. And now keep in mind that UU transpose is an M by M identity, and VV transpose is an N by N identity. Okay. So why is this singular value decomposition useful now? Well, let's actually consider how we can, first of all, figure out the U, sigma, and V transpose, and how, again, we can use it for reductions in certain cases. So first of all, if I'm considering, let's say I consider AA transpose. So now if I look at AA transpose, this, if I plug in the singular value decomposition for A, I get something that looks like this. So now, because U and V are orthonormal matrices, this term in the middle is the identity. And so I'm left with U, sigma, sigma transpose, U transpose. Great. So now what is sigma, sigma transpose? So this thing, let's again consider the case that M is less than N. So here we have M. We have M eigenvalues here. And this is sigma, sigma transpose. And then if we transpose this matrix, we of course have an N by M matrix, where I'm going to have sigma 1 up to sigma M, and then 0. And if I just multiply these two, I should get an M by M matrix. That's just sigma 1 squared, sigma 2 squared, sigma M squared. Okay. So now AA transpose, we've written it in the form U lambda U transpose. And now my lambda is just this matrix of sigma 1 squared, sigma M squared. Okay. So now this is great. Just as what we did for the eigen decomposition, we've actually just proved that these symmetric matrices here have an eigen decomposition of the form that we had in the last slide, which was just that here U takes the place of Q now. And we've also found something else, which is that the eigenvalues of AA transpose are just the squares of the singular values of A. So this is great. This is a nice, useful trick. So if I want to compute the singular value decomposition, one way I can do that is just compute the eigen decomposition of AA transpose, and similarly, A transpose A. So here we will get another matrix that's like another factorization that's like U V lambda tilde V transpose. And the reason I put a lambda tilde here is that if we write out what A transpose A is, this is going to be V sigma transpose U transpose, U sigma V transpose. Again, we do the same trick. U's are orthogonal, so this cancels out. And now sigma transpose is just this matrix sigma 1, sigma 2, M, and then a bunch of zeros. And then here sigma is now my usual matrix of sigma 1, sigma 2, sigma M, and a bunch of zeros. So now this is an M, N by M matrix here. Oops. And an M by N here. And so when I multiply this together, I get an N by N matrix, sigma 1 squared, sigma 2 squared, sigma M squared, and then a bunch of zeros at the end here. And that's why I have an extra. This lambda tilde is basically lambda, but padded with zeros. Okay. So by doing the eigen decomposition of AA transpose and A transpose A, there's a way to figure out what these U's and V's are. But of course, in this course, we're going to not do this by hand. We're going to do this by computer, and the relevant functions in NumPy are these eig functions. So in an actual library online, you'll use the eig function or the SVD function. And there's some exercises in the first homework that cover using these and checking some of the theoretical properties of these decompositions that will be useful. But again, the main point of these two decompositions that we're going to use in the course is that it allows us to simplify some recurrences that we'll see in lecture 2 for the analysis of linear regression. Okay. So moving on from decompositions, of course, I assume you have all heard of a matrix inverse, But I'm not sure how many of you would have heard of something called the Moore-Penrose pseudo-inverse. This is the Moore-Penrose inverse. You might hear me call it the Moore-Penrose pseudo-inverse or just the pseudo-inverse. But what is this and why do we care? Well, the Moore-Penrose pseudo-inverse is a way of effectively finding a solution to a system of equations, even when your system is no longer square. So what do I mean by this? So first of all, if I'm given a matrix A, that's an n by n matrix, and I'm trying to solve a system of equations that looks like ax equals b, if I know that A is invertible, I can just compute A inverse B. Okay, so now on the other hand, let's say I have now that A is an m by n matrix, and I'm trying to solve a system of equations, ax equals b, but now let's say m is much bigger than n. Or even just any amount bigger than n. So in this case, sorry, let's say n is bigger than n here. So in this case, the number of variables that I have in my regression is way larger than the number of equations. And so there's infinitely many solutions to this problem. In the second lecture on linear regression, we're going to be talking about how to find some of these solutions. But the question is now, if we want to solve a system of equations that looks like this, and we want to just find one solution, the way we can actually do this is by computing the pseudo-inverse. So there's a notion of inverse for rectangular matrices that we can actually use here to solve this. And so that's what I wanted to go into in this part briefly. So technically, if we want to, let's write out the definition for a pseudo-inverse first. Okay. So given A in m by n, the Moore-Penrose inverse, A dagger, satisfies the following properties. And these are 4 properties. Honestly, they're a little bit unintuitive, which is why right afterwards, we'll give a very intuitive formulation for the pseudo-inverse based on the singular value decomposition. And to just save space, I'll list 3 and 4 here. So what are these properties trying to get at? Well, these are all properties that are shared by, that are all satisfied for the normal usual inverse. And let's just check this. So first, let's say A is an n by n, and it has an inverse A inverse. And let's just check property 1. So we have A dagger is just going to be A inverse. And we have A inverse A is of course A, since these 2 terms cancel out. And the other properties are pretty easy to check, so I'll just leave you to it. Now the question is there a nice intuitive way of understanding what the pseudo-inverse is based off of another decomposition? And the nice part is that if we write out the singular value decomposition for any m by n matrix, so here let's say A is an m by n matrix. So for A m by n, if we have A equals U sigma B transpose, and recall sigma is this diagonal matrix, sigma 1, sigma 2, sigma m followed by zeros, then A pseudo-inverse is just going to be V sigma dagger U transpose. And now what is this sigma dagger? Well, this thing is just going to be 1 over sigma 1, 1 over sigma 2, 1 over sigma m, followed by zeros. Okay. And now why is this a kind of intuitive notion of inverse? Well, the nice thing is that if I look at this equation here, what exactly am I doing by writing the SVD? So if I take the SVD of A, I have U sigma V transpose X equals B. The first step is I'm writing it so that I multiply both sides by U transpose. That eliminates this U part here. And so I'm left with something that looks like sigma V transpose X equals U transpose V. Now, the issue is that sigma is a rectangular matrix that I can't exactly invert, but I can get kind of close to inverting it by multiplying it with this matrix sigma dagger. And in particular, what do we actually have? Well, sigma dagger, this is an R n by m matrix. So let's look at, and then sigma, remember, is an R m by n matrix. So what do sigma dagger look like together? So if I look at sigma dagger sigma, this is going to end up looking like it's an n by n matrix of just ones followed by a 0. So it looks like this upper component here looks like the identity in m by m followed by a bunch of zeros. So I've somehow kind of inverted the matrix sigma. And actually, if I write it here as sigma dagger, this is exactly the m by m identity matrix. And so in a nice way, I've found a version of an inverse for solving this system of equations. So here, what I would do above is multiply by sigma dagger next. And this will somehow kill off enough components. And then, of course, I would multiply by V afterwards. So eventually, I'll end up getting a solution that looks like X equals V sigma dagger U transpose V. Great. Okay. So that's all I wanted. I think that's pretty much all the material you would need to know regarding linear algebra and the decompositions that'll be useful for this course. I know that might have been a bit fast, but I hope that the text that I've given in the syllabus would be a helpful review of the material in case you need a bit more. Okay, so for the next part, we're going to be talking about aspects of analysis that will be useful for the course. And so there's three sort of aspects that I wanted to cover here. The first one is taking gradients. The second one is going to be norms and inner products. And importantly, some inner products on infinite dimensional spaces or inner product spaces, which are Hilbert spaces. Okay, so let's first of all begin with gradients, because one of the ways that we're actually going to train machine learning models in this course is by using something called gradient descent. So this is just an optimization method, a very standard optimization method for minimizing some loss function. But of course, we'll get into this in lecture 2 and 3. For now, what you would need to know is how to compute gradients of a multivariable function, and in particular, how to organize it in terms of a, maybe you're taking the gradient with respect to a giant vector or a matrix. And I think people typically call this matrix calculus, but here we'll see it's not so much more than an extension of what you've learned in multivariable calculus. Okay, so let's begin. If you have a function f from Rd to R, what we're going to do is compute the gradient of the function, which again is a function now from Rd to Rd. This is the gradient. And how do we actually compute the gradient? Well, the gradient of a function at any point x is going to be a giant vector of the partial derivatives of f of x with respect to every variable. And here I'll call my variables x1 to xd. So this is just a giant vector of these partial derivatives. And let's go over maybe one of the simplest examples of just a function in 2 dimensions. So let's just say I have f of x1 comma x2 is just x1 squared plus x2 squared. Then the gradient of f at any point x1 tilde x2 tilde is just, I compute the partial derivative of f with respect to x1. So partial f x1 tilde x2 tilde with respect to x1, partial f x1 tilde x2 tilde with respect to x2. Well, this one above, I've made it simple on my life, is just 2x1 tilde. The bottom one is just 2x2 tilde. And that's it, that's the gradient. Okay, so why is this a nice example? Well, you'll see that this actually generalizes quite nicely to the case where in d dimensions, let's say I now have f is a function on Rd, R given by f of x is norm of x squared. And here, this norm, which I hope you are all familiar with, but there's a nice review of norms in the lecture notes. This is just the sum from I equals 1 to d, xi squared. So this is a natural generalization of example 1. And if we go again and compute the gradient with respect to x here, well, we're going to have to take, and let's call this x tilde a new point. We're going to have to take the partial derivative of f at x tilde with respect to every example, with respect to every dimension here. And this, as we just saw before, is just 2x1 tilde, 2x2 tilde, up to 2xd tilde. Okay, so not much is new here, except that we can do a nice reduction. We see that there's this pattern of x1 tilde, x2 tilde, xd tilde here, and they're all multiplied by the same constant 2. So I just factor out that 2, and now this is just exactly the vector x tilde. So in shorthand, we found that gradient of f of x tilde is just 2x tilde. And this makes sense. This is a vector in Rd. And that's exactly the condition we had on the gradient here. It has to map from Rd to Rd. Okay. So this is typically how you would take gradients with respect to a vector valued function. You would first take the partial derivatives with respect to every coordinate, see if you can identify some clear pattern like we did here, and then write it out nicely. Let's just do one more example of something like this to make it even clearer. So let's again take f as a function from Rd to R. And let's say f of x now is W transpose x, where W is just a Rd dimensional vector. So keep in mind, I can also write this as an inner product here, W comma x, and we'll review what that is briefly in the next slide. And again, it's all covered in the lecture notes online as well. But now let's say I want to compute gradient of f with respect to x, and I want to compute it at a point x tilde. Well, what do I know about f? F is actually just summation wi xi, I equals 1 to d. So now I'm going to take this giant partial derivative. This is now, I take the partial derivative with respect to x1. This is just w1. I do the same for x2. This is just w2, all the way down to wd. And so very conveniently, it's just come out that the gradient of f at any point x tilde is just w. And just to double check, this is a vector in Rd. And so we're good to go. This is the gradient. Now something interesting has happened here. So if you remember, in the usual one-dimensional case, so let's say if you have a function g from R to R, and g of x is something like 5x. G prime of x, which is just the derivative, is just 5. This kind of looks like that. We have W transpose x, but the interesting thing is that when we had a transpose, we actually had to transpose it back to get W. And one intuitive way of just remembering this is that your dimensions had to check out at the end. Your gradient with respect to x has to be a function into RD, which is the dimension of x. And so we had to take this extra transpose. So something to keep in mind, and it's always good to do this dimensionality checking to make sure everything has worked out. But this is basically the notion of gradients that I would need you to know how to do for the course. And honestly, it will be primarily useful in lectures 2 and 3 for understanding this analysis of linear and kernel regression. But the main thing that I would need you to do, and this is the exercise that's required in problem set 1, is if I have a function that looks something like norm of wx minus y squared, where here x is some d by n matrix, and y is a 1 by n vector, and w is a 1 by d matrix, I would ask you to compute gradient of f of w, which is, this function is parameterized in terms of w. So at any point w tilde, I would need to know the gradient. And keep in mind, this will be a 1 by d dimensional vector. Okay. So again, the key trick to keep in mind is just to write out a simple example. And think about what we did here. We just actually started out with a 2-dimensional case. Instead of considering the general d-dimensional case, I would recommend considering the 2-dimensional case or 3-dimensional case. So you can set d equals 2, n equals 3, something like that. Write it out and see if you see a pattern. And think about even what happens in the 1-dimensional case. So if everything is 1-dimensional, I would have just wx minus y squared. Sorry, this is a function of w. If I take the derivative, I would get something like 2wx minus y times x. So your gradient, of course, should look very, very similar to this in d dimensions, but there will be some extra transposes that you have to keep track of. Okay. So now let's move on to the second part, which is understanding norms and inner products. And let's start with inner products. Okay. So I'm not going to actually introduce formally the notion of what is a norm. There's some conditions that have to be satisfied, and the same thing for inner products. There's some conditions that have to be satisfied. But I will just say for now, these are all again written in the lecture notes. So given a vector space V, usually I will write a subscript V or a subscript curly H here, but this inner product is just a function on V cross V to some field. And typically you can think about this as real values or complex values, something like that. We will actually mainly think about it as real values. And this has to satisfy a number of properties. And I can let you look up in the notes what's written there about it. But I just wanted to provide some examples here that will be useful for the course of what are some useful inner products. So let's just go over some of the standard ones you have seen. So if I take the vector space Rn, and I consider the usual inner product on Rn, what does this look like? So given u comma v as two vectors in Rn, this inner product u and v is exactly summation I equals 1 to n ui vi. Okay, and this is very much what you would have seen, which is just like u transpose v. All of these are the same. This is the standard dot product that you would have seen on the on a finite dimensional vector space. Maybe one example, which is a little bit more non-trivial, is what happens when you have a complex valued vector space. And you have the complex inner product. So if UV belongs to a complex vector space, it's again summation I equals 1 to n ui, but now instead of vi, vi is now a complex number. You're going to have to take the complex conjugate. And this is to satisfy one of the requirements of the inner product, that it has this anti-symmetry property, where if I swap the order of the elements of the inner product, I have to take this conjugate. It's conjugate symmetry, I should say. Okay. All right. So then now in terms of maybe some non-trivial examples of inner products on spaces, right now what we've considered so far are finite dimensional vector spaces for inner products. There's also notions of inner product spaces which are infinite dimensional, and these are called Hilbert spaces. So this is an inner product space. And I'm going to put here that is complete. And this notion of completeness is a notion in real analysis or functional analysis. It's not going to be super useful for this class since we're just going to work with examples. But generally, let me give you some natural extensions of what you have seen in finite dimensional vector spaces, which correspond to inner products on infinite dimensional vector spaces. So these are in some way infinite dimensional vector spaces. So as a third example, I'm going to write down the space little L2R. And what is this? This is going to be the space of sequences I equals 1 to infinity, I equals 0 to infinity. And where each of these AIs is a real valued number. So I'll just say it's contained in R, this set. Such that the summation of AI squared I equals 0 to infinity is less than infinity. So this is a bounded sequence, bounded square summable sequence. Okay. And now what is the inner product on this space? So if I'm given two sets of sequences, the reason we're considering this one, and I do it in little L2 of R, this inner product is exactly what you have seen before for the finite dimensional case, but now we have an infinite sum. So we'll have an infinite sum of AI BI. And if you're familiar with some functional analysis, you can check that this sum will always be infinity if this property is satisfied here for both A and B. And this follows from this Cauchy-Schwarz inequality. But you don't, if you're not familiar with that, it's totally fine. It's not relevant to the understanding here of how we're going to use this in practice. Okay, and to make this a bit more concrete, let me just give one example. So let's just say U is this sequence 1 over 2 to the I for I equals 0 to infinity. So if I look at the squares of some of the sequence, so first I have to check, does U belong to L2 of R? And it does. So I'll have summation I equals 0 to infinity. 1 over 2 to the 2i is just summation I equals 0 to infinity, 1 over 4 to the I. And for those of you who remember geometric sums, this is just 1 over 1 minus 1/4. This is 4/3. So this is less than infinity. I'm good to go. Now let's say I take V from I equals 0 to infinity. Again, this is in L2 because if I do now 3 squared I, this is going to end up being 9 over 8, which is less than infinity. So both of these are in this in this space. So if I look at U inner product V, this is just going to be the sum from I equals 0 to infinity, 1 over 2 to the I times 1 over 3 to the I, which is just I equals 0 to infinity, 1 over 6 to the I. And of course, we can evaluate this again. It's just 6/5. Okay. So this is just one example. Actually, it will be a very useful example because we'll use it in a lot of our neural network, infinite width neural network computations. So it's good to have some familiarity with what this vector space is, but really it's a kind of a trivial extension for now. In terms of just the applicability, it's just a very simple extension of the space here that you need. Okay. So now maybe here's a non-trivial example. And let me just double check my example numbering. So this will be example 4. And this will be inner products. Right now we've considered inner products on sequences, but we want to do inner products as well on functions. So this will involve the space L2, and we'll do again L2 of R for now. Okay. So I'm going to take the most general notion of L2 of R. So I'm going to say a function f that's real value belongs to L2 of R if integral negative infinity to infinity f of x, here I'll take f of x squared dx is less than infinity. And what does this actually mean? Well, why do we choose this? In some way, it's a continuous version of the sum that we had in the previous slide. But of course, this will rise in functional analysis a lot as a convenient space. And the reason we want to consider this L2 of R is that there's actually a nice inner product on this space. So I'm going to define for any two functions f and g. So f and g belong to L2 of R. I'm going to define the inner product of f and g in L2 as this integral, just as we did for sequences where you had ui vi. Here we're going to have f of x gx dx. And so you can check that this actually satisfies all the necessary properties of an inner product from before. If you're working again in the complex space, if you have functions on, instead of R, you have functions on complex numbers, you'll have to take a complex conjugate here, but we won't have to worry about that in this course. In this course, we'll always have real valued functions. Okay. And in the problem set, there should be some examples asking you to compute some of these integrals. It's really not so bad. It's just what you have done in multivariable calculus of computing the integral of some function. In fact, in the homework, there will be another useful space, which I will denote. This is in the homework. You'll run into an example of something which I call L2 of mu. And we'll see that f belongs to L2 of mu if integral from negative infinity to infinity f of x squared. Well, let me write this constant inside. 1 over root 2 pi e power negative x squared over 2 dx is less than infinity. This is a much larger class of functions. It's kind of easy to check that if a function belongs to L2, it very easily belongs to L2 of mu. Okay. And why will this be useful? Well, this type of integral will actually come up in the computation of kernels associated with neural networks. Of course, most of these integrals have already been done for us, so we won't have to worry about actually doing the integration, but it's at least good to be familiar with how this is arising. And one thing that I will mention that's a nice segue to the next topic is that this component here that we're multiplying by is effectively the density function of a Gaussian, of a standard normal. And so you can very easily think about this L2 of this norm here that I've written out as the expectation of f of x, where x is the is a sample has density being the standard normal Gaussian. So this might be a little confusing at first, but let's actually just transition now into the probability segment of the course and what I would expect you to know from here, and we'll see concretely what is useful and how to also evaluate some integrals like this. We'll go over some concrete examples. Okay. So the last thing I would need you to know is some basics of probability theory. And I'm not going to go into all of the terms here at the moment. But what I will do is go over some key notation that I'm going to use in the course. So of course, I expect you to know what a random variable is. So this is let's say x is a random variable. And in fact, let's also consider the case where x has a density. So I'm going to consider x is drawn from some density. And I'm going to use the probability of x obtaining a value small x, curly x here. This is going to be my notation. And this is the probability that capital X equals little x. And so here, of course, if x is a discrete random variable, this is called a probability mass function, PMF. If x is continuous, we'll write it as a probability density function, PDF. This will be a probability density function. Okay, and so there's some key properties that make things a probability, and one of them is that the probability of a variable obtaining element in the whole space has to be 1. And this, for a probability density function, this is just integral over the support of the probability of x. So let's say the support is the real line, which it will be in most of our cases. This is just 1. Okay. I would expect you to know what the expectation of a random variable is. And maybe I'll write it here as expectation of x. Okay. And I would also expect you to know what are moments, which is just the expectation of higher order values here of a random variable. So this is the expectation. Here you have moments. Okay. And let's just, of course, I'll also expect you to know things like variance and covariance. Okay. And just remember, I mean, maybe a quick example here is just that if I have two random variables, x, y, which have mean 0, so their mean being expectation of x equals expectation of y equals 0, then their covariance, well, first of all, their variance is just expectation of x squared. And the covariance is just going to be this expectation of xy. Okay. Great. So let's just go over some of these computations now for the Gaussian distribution. And in particular, I would want to go over some useful integration techniques for this. So how can we use some of these facts, like what is the expectation or density of integral of the density of a Gaussian, to evaluate some integrals in a nice way. So let's go to the Gaussian distribution, the Gaussian or normal. And here I'm going to consider the standard. So the standard Gaussian distribution is going to be one with mean 0. So expectation of x is just going to be 0. and the variance is going to be 1. And in fact, because it's mean 0, we have this property for the variance, expectation of x squared is just going to be 1. Okay. And in these cases where it's clear what the random variable is and what we're taking the expectation over, I'll usually drop this subscript. But in other cases, like when we do computations with the neural networks and corresponding kernels, I will write it out clearly to make sure what we're taking expectation over. But what does this actually mean? So first of all, what is the Gaussian distribution? Well, the probability density function looks something like this. So the probability of x obtaining some value small x is just 1 over square root of 2 pi e power negative x squared over 2. And in general, I think most of you have seen it. If you have a mean mu and a standard deviation sigma, then the density function would have been 1 over square root of 2 pi sigma squared e power negative x squared over 2 sigma. Okay. So this is your density. Next, how do we actually write these expectation and variance terms? Well, first of all, we have, because the density has to be 1, we know now for a fact that this integral better be 1. And there's a nice proof of this in the lecture notes by taking an integral in 2 dimensions and using some polar coordinates to figure it out. The second fact is now from the expectation, we also know that e power negative x squared over 2 times x, this had better be 0. This one is actually a bit easy to figure out. Why is this 0? Well, if I just look at this, if I call this f of x, it's easy to see that f of negative x equals f of x. And if you remember from calculus 1 and 2, if you have an integral of an odd function over the whole real line, this integral better be 0. So that checks out. Now the last thing is we also know from the variance that x squared e power negative x squared over 2 dx equals 1. Okay. So we have somehow these 3 facts. And now we want to use some of these, primarily this one, to evaluate some non-trivial integrals. And so let's go over a nice example. So how to compute the moment generating function, which is given by e power tx, for some, let's say for some positive x. I'm going to write this. We know what the expectation is just by definition. This is e power tx, e power negative x squared over 2 dx. How do we compute this? Well, it looks tricky at first. There's a lot going on in this integrand, but the key thing to recognize is that we can use this trick of completing the square to evaluate this integral and use the fact that the integral of the density of the Gaussian is 1. Okay. So let's begin. What's the first thing I'm going to do? I see that this can be written as e to the negative x squared over 2 plus tx. Now, I want to try to make this a perfect square. And so to do that, I need to add some terms. And so what will I add to this? So let's say I end up adding a t squared over 2, and I want to subtract and then add a t squared over 2. Actually, let me do this in red so it's clear. This will be dx. Okay, so just writing this out very systematically, I should get negative 1/2 x squared minus 2tx plus t squared And then on the outside, I'm left with a t squared over 2. Okay, but now this is good. This term here, we can clearly see, is x minus t whole squared. And so if I try simplifying everything out, this part here in blue does not depend on x at all. So I'm going to also just pull it out of the integral. And I'm left with e power negative 1/2 x minus t whole squared dx. Okay. So now here's the nice fact. You can do this either by u substitution or whatever trick you want. But what we can do is look at the terms here and here and recognize that everything in the blue is the integral of the density of a Gaussian with mean mu equals t and variance or standard deviation 1. And the integral of any density better be 1. So we can just say all of the terms in blue cancel out to 1, and we're left with e power t squared over 2. And we're good to go. So this type of problem, I hope, makes clear that you can do all kinds of crazy integrals, just knowing the fact, especially if you ever see an integral that has this e power negative x squared over 2, it should kind of flash lights in your mind that say, this looks like the integral over some standard normal. And so you should always try to use a trick like this to get around it. And in fact, there's several examples in the problem set where you have the opportunity to try out this trick, and some of them will be required. The key thing with this, though, is that you can see the computation is literally here only 3 steps. And that's how it should be for almost all the examples in this first problem set. It should really only be 1 line or 2 lines of computation. If it's any more than that, then somehow something went wrong in the calculation. So please keep that in mind. But this will be a useful trick that we'll actually use when computing exactly what the kernel corresponding to infinite width networks looks like. And of course, we'll get to what all these terms mean. What do kernels mean? What is an infinite width network? We'll cover those starting lecture 3 onwards. But I hope this has been a brief introduction and a good introduction to this math background that's required for this class. And with this, I hope to see you in the next lecture, where we'll actually start the fundamentals of the course with linear regression. And thanks, and see you in the next lecture.